Earlier, we saw how the sign, the sign of the derivative, encoded whether the function was increasing or decreasing. Thinking back to the graph, here I've just drawn some random graph. What is the derivative encoding? Well, here at this point A, the slope of this tangent line is negative, the derivative is negative, and yeah, the function's going down here. At this point B, the slope of this tangent line is positive and the function's increasing through here. Right, the derivative's negative here and it's positive here. The function's decreasing here and increasing here. So that's what the derivative is measuring. What is the sign of the second derivative really encoding? Maybe we don't have such a good word for it, so we'll just make up a new word. The sign, the sign of the second derivative, the sign of the derivative measures concavity. The word's concavity, and here's the two possibilities. Concave up, where the second derivative is positive, and concave down, where the second derivative is negative. And I've drawn sort of cartoony pictures of what the graphs look like in these two cases. Now note, it's not just increasing or decreasing, but this concavity is recording sort of the shape of the graph in some sense. Positive second derivative makes it look like this. Negative second derivative makes the graph look like this. And I'm just labeling these two things, concave up and concave down. And this makes sense if we think of the second derivative as measuring the change in the derivative. So let's think back to this graph again. Here's this graph of some random function. Look at this part of the graph right here. That looks like the concave up shape from before where the second derivative is positive. So we might think that the second derivative is positive here. That would mean that the derivative is increasing. What that really means is that the slope of a tangent line through this region is increasing. And that's exactly what's happening. The slope is negative here, and as I move this tangent line over, the slope of that tangent line is increasing. The second derivative is positive here. You can tell yourself the same story for concave down. So look over here in our sample graph. That part of the graph looks like this concave down picture where the second derivative is negative. Now if the second derivative is negative, that means the derivative is decreasing. And yeah, the slope of the tangent line through this region is going down, right? The slope starts off pretty positive over here, and as I move this tangent line over, the slope is 0 and now getting more and more negative. So in this part of the graph, the second derivative is negative. What happens in between? Where does the regime change take place? So over here, the second derivative is negative. Over here, the second derivative is positive. There's a point in between, maybe it's right here, and at that point, the second derivative is equal to 0. And on one side, it's concave down, and on the other side, it's concave up. A point where the concavity actually changes is called an inflection point. Right? It's concave down over here and it's concave up over here, and the place where the change is taking place, we're just going to call those points inflection points. It's not that the terminology itself is so important, but we want words to describe the qualitative phenomena that we're seeing in these graphs. Inflection points are something you can really feel. I mean, if you're driving in a car, you're braking, right? That means the second derivative is negative. You're slowing down. And then suddenly, you step on the gas. Now you're accelerating. Your second derivative is positive. What happened, right? Something big happened. You're changing regimes from concave down to concave up. And you want to denote that change somehow. We're going to call that change an inflection point.